All right, so we've been talking about momentum, and what we're going to talk about today is a little bit about what you learned when you were doing the PhET collision exercise, which you were supposed to have somehow indicated to me that you did. If you need to show it to me at the end, you can show it to me at the end. I think Zoe sent it to me, so that I know that you did that. And what did you find? There were collisions, there was velocity being moved around, but what was actually the quantity that was conserved? Momentum. Okay, so linear momentum, which we were talking about, and we talked about how it's that lowercase p, and you have to be careful that it's a lowercase p and where you put your equal signs. What is that equal to? What's p equal to? Not mass times volume, mass times velocity. Okay, because it's a vector. All right. Okay, so note that momentum is a vector. It points in the same direction as velocity. Note that because it's a vector, we talk about the vectors in each, we talk about the momentum in each direction separately. And as we'll talk about in a minute, that means that we can conserve the momentum in each direction separately. We talked a little bit about how the units for momentum are nothing special. They're just kilogram meters per second, which is what you get when you multiply together the units for m and v. And so what you were kind of supposed to figure out from the PhET collision exercise that you were doing on Friday is that the total momentum of a system, or the total linear momentum, because later on we'll talk about other kinds of momentum, that the total linear momentum of a system stays the same or is conserved. I will make my caveat in a moment. Okay. And that system has to be closed and isolated. And we'll talk about what each of those terms really means. So closed means no mass enters or leaves the system. Oh, how cool. So that means that if one block is going to slide into another block, that you better make sure that your system includes both of those blocks. And isolated, anybody have an idea what isolated is going to mean? Yeah, no external force. Good. Okay. So we often end up saying that the initial momentum is equal to the final momentum. Or we could say that whatever that is equal to a constant. And when we're talking about initial and final, or before and after, there's always some kind of event. So when I take my Newton's cradle and I lift up one of the balls and I say that the momentum is conserved before and after the collision, and that's why if I lift up one ball pops up on the other side. The event is the balls colliding. And usually the event will be a collision. However, we may talk about momentum in terms of things like objects swooping around planets, satellites swooping around planets and taking what we would call a gravity assist. And that has to do with momentum. And in that situation, the satellite isn't necessarily colliding with the planet, but there is an interaction that's changing the momentum. So while it will usually be a collision, you don't want to get yourself so convinced that if there's no collision, there's no momentum, because that won't always be true. Okay? All right, we good? Okay. Then let's do some examples, because I really think that's kind of the best way to play around with this. So let's start with sample problem 18. If somebody wants to read it for us, I'm going to copy out the table here. Yes, should be the one with the table. Okay, so you should have the table. I'm just writing it again so that I can point at it. Okay. That's what I means. It's a unit vector, but I can't draw it with the caret over it, so it should have been bolded to be a vector. Okay, so it's really important when you're doing momentum problems to draw a picture. Okay, so that you know what before is, you know what the event is, and you know what after is. So everything is moving along the x-axis because all of the vectors have a unit vector I. So I'm just going to make one nice big long x-axis. And initially, or before, I have a great big object, right? That's A plus B plus C, because my object initially starts together before it breaks into pieces. And which way is it moving? Well, what does it say in the problem? Yeah, so it's going to be, I'm going to give it just a VI because the whole object really only has one velocity. Whereas we said VI is negative 0.40 meters per second I hat. Well, I'm going to put after over here. Okay, so there's my event, which is the little springs releasing and breaking the object into 3 parts. And then over here, I'm going to have my final, or my after. And now my great big object that was A plus B plus C is now 3 smaller objects. And I know what objects B and C are doing, right? What are objects, which direction are objects B and C moving in? Okay, so I'm going to put object C in front because it's moving faster. And then I've got object B. And then I have object A. But I have no idea what object A is doing. And so that F subscript indicates that it's after. And then each of my objects has their own velocity. So for instance, if I just go back up to my table, this is going to be VFB, this is going to be VFC. So if this is a closed system, which it is, none of my mass is leaving or entering. If it's an isolated system, which it is, there's no hockey stick coming down to push one of the pieces somewhere else or a pool cue or anything. Okay. Then that means that the total momentum of the system is conserved, which means that I don't know, he's watching YouTube. Whatever momentum I have before is the same as the momentum that I'm going to have after. Sure. Magnitude and direction, because momentum is a vector. It might have been. The velocities might not necessarily work out because velocity isn't conserved, but mass is. Okay. So what direction does all of my momentum point in before my event? Negative x direction. So where does all of my momentum have to point? I'm sorry, where does my total momentum have to point after my event? In the negative direction. What direction are A and B moving? Positive. So A and B are going to, B and C are going to have positive momenta. So what direction does the momentum or the velocity of mass A have to be in? Negative. And it's probably got to be pretty big, because not only does it have to compensate for the positive momenta of B and C, it still has to make up whatever that initial momentum is. So we could make a guess and say that VFA is going to be that way. A prediction, something that makes sense based on the stuff that we know. Okay. So again, when you're drawing these diagrams, it's really important that you clearly label, for your sake and the sake of the grader, what is before or initial and what is after or final. Okay, just as when you were doing conservation of energy problems, it was really important to label which two locations you were comparing the total energy for. Okay, so now we know that our initial momentum has to be equal to our final momentum. This is only in one dimension, so I don't really have to worry about breaking it down into x, y, and z. And initially, I just have my total mass times that initial velocity, because my object is still all together. But afterwards, I'm going to have the mass of A times V final A plus the mass of B times V final B plus the mass of C times V final C. And what am I trying to solve for? VFA. So I'm just going to take everything else that doesn't have VFA in it over to the other side. And then I'm going to divide the whole thing by the mass of A. Now note that in this situation I have not removed the vector symbols from my velocities. So when you substitute in, you need to put in the pluses and the minuses. Okay? So the total mass is, if we add up the masses of all the pieces, and I think that's going to be 1.30 kilograms times the negative 0.40 meters per second. The mass of B is 0.6 kilograms, and its velocity is 0.2. And then the mass of C, bless you, is 0.2 kilograms, and its velocity is 0.3. And we're going to divide that by the mass of A, which is 0.50 kilograms. So VFA will be let's see what other people got. Make sure you get all your parentheses in the right spot and all that jazz. Okay. Gianni, are you in the calculator seat? Did it migrate over to you? Oh. Well, it should. Just try it again, Gianni. Just try it again. But it should, in fact, be negative 1.4. Okay. All right. So note that it is, in fact, in the negative direction, as we predicted, because it has to not only compensate for parts B and C that are moving in the positive direction, but then it actually has to have as much additional momentum in the negative direction as it had initially. Okay? Make sense? Got it? Okay. So I also want to talk briefly before we do our next example, just so that you have it, that sometimes we talk about the momentum of the center of mass. And that comes up on questions. It comes up in physics examples, AP questions. And it's actually sometimes a very helpful way to write what the total momentum is going to be. Because, of course, I could write the total momentum as the initial momentum of all of my objects. And just for simplicity's sake, I'm going to say there's two of them. Okay? But I can also say that this is equal to the total mass times the velocity of the center of mass. And sometimes, although not probably as much for what we're going to do, but when you're applying conservation of momentum, maybe to a rocket ship or to things in astronomy, sometimes we really do need to know what the velocity of the center of mass is. That is really the value that we want. So we can solve this algebraically and say that the velocity of the center of mass is the total momentum, depending on how you want to write it, divided by the sum of the masses. And we can add more terms if we have more than just the two objects. What's up, Zoe? We've been solving for the velocity of individual objects. Yeah. No, the center of the center of mass of a system. So if I had two objects, and this has some interesting let's see if I can actually find it real quick. I don't think that's it. I can't. I wonder if it's here. It shouldn't be. Everything got moved over. No. I can't find this simulation quickly. For instance, if I had a 1 kilogram object and a 1 kilogram object, where's the center of mass? In the middle, right? Well, if those objects were each moving towards each other at 1 meter per second, how would the center of mass move? It wouldn't, because I'd have P1I would be 1 kilogram meter per second. P2I would be negative 1 kilogram meter per second. And when I found the total momentum, it would be 0. And that would be equal to the total mass times the velocity of the center of mass. So in a situation like that, maybe what I really care about is what the center of mass of the system is doing. If they were both moving in the other direction, that would be different. So if I had my 1 kilogram mass and it was moving this way, and I had another kilogram mass moving that way, again, where's the center of mass? All right, so again, it's going to be in the middle, but if both of those objects are moving at the same constant velocity, what velocity is the center of mass going to have? Yeah, it's going to have that 1 meter per second. That the whole system and the center of mass is going to do that. Now, we can make it more complicated. If that one's moving faster, then what's going to happen? What's going to happen to the objects if this one is moving faster? Well, this object is going to be moving faster, so the distance between the objects is going to get bigger, right? The center of mass is always going to be in the middle, but being that the objects are getting farther apart, the center of mass is going to be moving with respect to the objects. So now the center of mass is going to have a velocity. It should, I think, have a velocity of 1.5 meters per second. Okay, so it's going to be moving with respect to both of the objects. Okay, so when we're talking about the velocity of the center of mass, we're talking about the center of mass of the system. Okay, make sense? It just shows up a couple times. All right, so I definitely think we can get through sample problem 20, and then we'll see if we can start the other one. Okay, so if somebody could read that for us, please. Okay. So if you thought about it in terms of my Newton's cradle balls hitting, especially if we only thought about two of them, right? When those objects hit, they exchange momentum. Are they exchanging all of their momentum? Yeah, pretty close, okay? Because after the hit, the one that was initially moving is now stopped temporarily. Pardon me? Yes, no velocity means no momentum. So why do you think the total, why is there this total transfer of momentum, this complete transfer of momentum? Yeah, because they have the same mass, okay? So it's a little different in this situation because my meteor that's coming in has a very different mass than the Earth. And this is what we'll talk more about collisions on Wednesday. But this is an example of an inelastic collision because the two objects are stuck together at the end. Actually, it's a complete inelastic collision because in a complete inelastic collision, the objects are stuck together. Our last example where the object started as one piece and broke into three pieces is also a complete inelastic collision. We'll talk more about this later. But we're going to assume that we're in the reference frame of the Earth. So the Earth is not moving. Okay, so we'll let the Earth be m2 and we will pretend that v2i is equal to 0. And because I can align my axes any way I want, I'm going to make an axis so that the meteor and the Earth are all along the positive x-axis, just because it makes my life easier. Yeah, that's what we're going to do right now. No, it is a meteor, but it's the same thing. Substitute in the moon if you want to substitute in the moon. Okay? Well, there's going to be a lot more problems if the sun crashes into the Earth. Because the moon, and really, honestly, because the moon and the meteor are both pretty much hard, and the sun is a fluid. And so that makes everything a lot wackier. You need a computer. And nobody here was in astronomy this trimester because we just saw what would happen if two stars collided with each other. We were watching a video. Okay, so what's my initial velocity of my meteor here? What was it, 7,200 meters per second? Positive, again, in the x direction. So this is my before, or my initial. Afterwards, on a much smaller scale, simply because I can't make it fit, my two objects are stuck together. So this is going to be M1 plus m2. And they're going to have some velocity that I'm just going to call v final because there's only one velocity here. And then this line down here is my after or my final. And again, you really need to clearly label your picture both for your own sake and for the sake of the person who's trying to follow what you did. Okay. And the event, of course, is the collision. All right, everybody got what they need? Good. All right. So I'm going to say that my momentum before is equal to my momentum after. It's the momentum of the whole system, but I try to avoid using capital P's unless I absolutely have to. And then I like to write down the momentum of each of my objects. So I have P1I plus P2I. I've only got one object after, so it's still just going to be PF. You know that at the beginning I like to give you guys probably more notes than you need, but it's better than taking shortcuts. Okay, so then I've got M1 V1I plus M2 V2I is going to be M1 plus M2 times VF. And I can get rid of something here, right? Right, because my Earth is initially at rest, so V2I is equal to 0. It was on your picture. So if what I'm looking for is VF, that's going to be M1 V1I divided by the sum of the masses. And in case you forgot, the mass of the Earth is 5.98 times 10 to the 24th kilograms. I'd make you look it up, but I'd like to finish this problem before the bell rings. And then what do we get? Well, actually, before you start calculating things, what do you expect the sign of VF to be? Positive, because? Yeah, the sign of the original momentum was positive because that's the direction my meteor was moving in. It's actually a meteoroid, but we're not going to get crazy. I get 6.02, but I'm not going to. See what everybody else got. So, did we feel it? Did we move? Did the Earth move? No, not really. Okay, why? It's because the Earth has such a big mass that it dominates the situation in terms of momentum. It couldn't not move at all, but it's effectively not moving at all because the velocity is so small. All right, there we go. See you tomorrow.